short enough, and Shubha has prepared for a certain length, so you should get his time. Welcome everybody. I'm excited to see so many students. We have run seminars with far fewer people in the room, so this is good. Shubha is also looking forward to discuss with you. So please take advantage of an opportunity of roughly 10 minutes discussion time at the end of the talk. Shubha will give his confirmation seminar. Confirmation is due at the end of the first year of a PhD. At this stage, the student should develop a clear proposal for what they want to achieve in the 3-year candidature and give us an idea of their preliminary work and their work ahead. Type this over there, and over to you to introduce the class to what you have in mind.
Good afternoon, everyone. My name is Shubhra Shankar. I'm from India. I'm a first-year PhD student at the Department of Infrastructure Engineering. So today, this is my confirmation talk. As you can see, the subject is the statistical inference between traffic volume, travel time, and origin destinations flow. And I'm doing my PhD under the supervision of Professor Stephen Winter, Department of Infrastructure Engineering, Dr. Martin Tomko, and Professor Nilal Ganguly as my external supervisor. So these are the contents for today. So we'll briefly look into the introduction, some motivations, research questions, then we'll go to the preliminary works that I have done in my first year, then we'll look into some future work and research plan, and with research output, we'll conclude the seminar. So this is the outline of our first section. We'll start with the motivation. So basically we know that origin destination matrices are very important and essential for transportation planning, strategic management, and future investments. Hence, the accuracy of the estimation depends on the multiple sources of data. Mostly they are the survey data, prior observed trips, or camera-based sensors, or a CSV computing device. These data are usually used to track the vehicles in a city. But the lack of data leads to erroneous estimation. Hence, lessening the data dependency is very important for estimating origin destination flow. Now, traffic counts and travel time, these are relatively less expensive data to capture, obtain, and maintain. So the goal of this talk and this confirmation report is understanding the statistical inferences of traffic counts and travel time on OD flow estimation problems. Here is the brief flow diagram, how the OD flow estimation is helping the transportation planning, traffic management operations, etc. And there are some research gaps that have been identified based on the previous literature. So the travel time and traffic counts being the less expensive inputs to obtain OD flow estimation, there has been significant research gap in estimating OD flow from traffic counts. There has been research gap to estimating OD flow from travel time only. And also there is a research gap to estimate travel time and traffic counts as a dual problem, estimation of each other from one of the other input. So the main research question, we have identified 3 research questions here. How to infer OD flow from traffic count data only? Is there any statistical inferences between travel time and traffic count? Is it possible to establish a transferable mathematical relationship between traffic count, travel time, and OD flow? So we have identified few researches based on these 3 research questions. So we know that Internet of Things based technologies are used to collect important transportation data. And these data sources are GPS data, sensor data that I've already discussed, camera sensor, count detector, etc. Along with these historical trip data that are recorded, they are also have been found very important input for OD flow estimation as well as traffic count and travel time prediction. But the challenges lies in this data collection, this data privacy, the data pre-processing, data storage, and data opening. So the link count data are found less expensive and less privacy sensitive, given that in the link count data the user information has been hidden. It's only the count of the vehicles that crossing an intersection. Hence, these are the approaches that we have found in this research. We want to estimate the OD flow in a road network using the link count data only. We want to provide a transferable methodology to estimate travel time using link traffic count data, and identification of the statistical inferences between this link count data and link travel time. So the main goal is to find some transferable mathematics, and these are the 3 research goals that I have identified for my research. First research goal is estimating OD flow only using link count data. Second research goal, estimating link travel time from link count data. and estimating link count from link travel time data. So I'll go to the preliminary work, what I have done in my first year of my PhD program. And these are the highlights of this section of discussion. And in my first preliminary work, I have done the OD flow estimation from link count data only. So I'll give you some brief highlights of the work. We have estimated the inter-arrival rates among the OD pairs using a network tomographic model that initially has been developed for computer networks. And we have developed some physical conditions and constraints on that model. We have validated that estimated count using the observed data that we have collected. We have made the data eligible for a microscopic simulation, and we have made a comparison with the model outcome travel time with the real observed travel time for the different sets of data. So these are the main constraints that we have in our model. We have assumed that the inter-arrival rate is constant over a small time interval. We have also assumed that all vehicles must be in the space-time cone in that particular interval. We have also assumed that all vehicles may route along any of the shortest path with equal probability. The OD pairs can be approximated using the nearest intersection, though that might be a true case because a vehicle's OD pair can be lies also in the between of the intersections. So our major contribution lies in predicting OD flow from link count data using the network tomographic model. We evaluated the travel time from OD flows using a microscopic simulator. We proposes a validation technique to evaluate the accuracy of the estimated OD flow. We include the unobserved public transport vehicle counts separately in our model. So this is the block diagram of the OD flow model that we have built using the link count data. We have the observed link counts. We have the road network topology-based model database. We have used them in the network topographic model. We have estimated the OD flow from there. Then we fit that information in the microscopic simulator. Now, I'll briefly come to the theory part. So let's say G is a directed and weighted network graph. Nodes are the intersection in that network. Edges are the road segments. And for if there are n nodes, we know that there are n into n minus 1 possible paths between any pair of ODs. And I is the total number of links available in the network, and k is the total number of the days for a specific time interval. Let's say I consider the 8 am to 8:15 am for 30 consecutive days, so k will be 30. And xkj is the number of cars between a particular OD pair j, that xk is for the kth day. And we have assumed that this is a Poisson distribution with the inter-arrival rate of lambda j. I'll come to the explanation part later. So for the time being, just understand that we have some link count data that has been vectorized by yk. We have the OD flow vector that is been vectorized by xk. We have the inter-arrival rate that has been vectorized by lambda. And these are the basic equations. Now, I'll show you some illustrative example of that. Let's say this is a road network. This has 6 road junctions or 6 nodes, and it has 7 links. And for a particular OD, I can consider AB as a OD, AC as a OD, or AF as a OD. So there are these combination of ODs are possible. And you can see if I consider A and F as an OD pair, then there are 3 possible routes from A to F, and that is AGEF, ABEF, ABCF. And in these 3 routes, I can divide the probabilities. If I want to go from A to F, then there is the probability that A to D and A to B will be 0.5 and 0.5. This is the initial assumptions that based on our constraints. And you can see if I build a matrix where the rows are the links and the columns are the origin and destination pairs. So as mentioned earlier, J will be the number of columns that I can have in the matrix, and I will be the number of rows that I can have in the matrix. And in this case, I have 7 rows, and I have let's say there are J number of columns. So I have initialized the matrix with these probabilities. Up to this part, this matrix is called the initial routing matrix, or A. Now, if I want to know what is the contribution of a particular link, let's say for a particular OD pair AF, what is the contribution of that link EF, I have simply calculated the conditional probability for that part. And you can see I have for the contribution of that EF link, or for the AF intersection, which has been initially was 1, you can see that EF row and ODAF column, it was 1. In the next figure, it becomes 0.75, calculating the conditional probability. So Now, the A matrix converted to the P matrix, where you can see the significant changes in the each contribution of the probabilities. So we have first developed the initial routing matrix as the A, which is the I into J, I cross J matrix. Then we have developed that equation, Y should be A into X, and these are the initial matrix where I have explained in the last illustrative example, and this is the condition that I have described in the constraint part. And so the matrix P, I have used the Markov chain model to build that matrix P from matrix A. And this is a simple using the state transition matrix. This is a simple formula, and we have come up with the final equation where I can write these equations where the expected value of a link count is the probability matrix that I have built with the interarrival rate vector. Now, we have also introduced the covariances, because in this matrix, the number of rows are significantly smaller than the number of columns, and there are infinitely many solutions possible that we know. And hence, to increase the number of rows, we have also considered the covariances part, and where I have simply calculated the covariances of the links, and for the probability matrix, I have developed a different matrix called B, where I have multiplied the rows by one. So for S11, it represents the multiplication of the P11 element and P11 element. So it's just by element multiplication. For S12, you can see this P21 into P11. Thus, I can increase the number of rows to get more number of equations to get a better accuracy in the estimation. This is the simple part, I think. Now we have plugged those two matrices together with the previous equation, and you can see this is nicely formed equation where I have more number of rows and I can estimate a better solution than what I have earlier. And I have used the expected maximization algorithm to estimate my lambda j's. I won't go over details into that because I don't have any time left. So spatiotemporal constraints that we have developed, because this is space and time need to be considered in a traffic situation. So the time gap between each inter-arrival has been considered as an exponential distribution that we well know from statistics. And delta t, let's assume that delta t is the time gap between two consecutive arrivals, and t min is the minimum time to reach its destination. Then this is a simple equation that we have developed. What should be the minimum time between two cars leaving an origin reaching its destination? And I have illustrated it with a simple example. Let's say I have a 7 cars in 10 minutes of interval. The lambda j would be 7. And if I assume that this is 3 minutes, the car will take from its origin to reach its destination. So all the vehicles in that particular 10 minutes of interval should reach its destination within that 10 minutes. Hence, I can draw a simple diagram where I have shown the time interval in the origin, and I am showing that the 7th car must leave as it can take more 3 minutes to reach its destination before the 10 minutes. So this should be the inter-arrival rates of the car. Each of the cars should come one after another, having a delta t of 1 minute. So these are the data requirement part where we need these data to build our model, to implement our model. And the WASM data means the OpenStreetMap data that has the nodes and edges, the traffic count locations. We have used the SCATS data. That's why we need the unique SCAT ID that is been identified the unique road intersections. We have the traffic signal configuration data. We have the signal volume data, and we have the PTV GTFS data for the public transport vehicles. So this is the flow diagram for the model, and this model is actually estimating the inter-arrival rates and then feeding to the simulator. So we have the Victoria's open data, and we have collected the SCAT IDs. We have estimated the arrival rate. We have built a bipartite graph for the SCAT nodes and the WASM nodes, and we have used that information for the route generators. That is a simulation enable input for the smart simulation. So this is you know that this is a Melbourne part of the section where we have used this map area for our model, and these numbers are the unique road intersections that where I have the traffic counts collected, because we have the sensors installed in this particular locations, and we have developed this graph from that identified location and known as the SCATS graph. And we have used all possible combinations of this road intersection as origin and destinations. There are 480 some combinations there, and there are 55 links in this network, and we have used that for our rows in the matrix. Then we have run the arrival rate estimator, and we have produces the results for the smart simulation, and we have compared that result in the next slide. So the estimation that I did from the model, I have made a simple comparison with that with the observed data, and you can see the estimator is nicely estimating the number of counts in the road intersection. So this is just an example. Within 8:45 and 9 a.m., we have observed the number of counts in a particular road intersection, and using the same data, we have estimated the number of ODs and used the data for the estimated observed counts, and these are nicely agreeing with each other. Next, we have used the estimated input for the simulation, and we have estimated the travel time from the simulation, and we have the real simulation observed from a Cytic database. Cytic is a company who is a navigation app where we have some access to those data, and we have made the real-time comparison with the data of the Cytic, and also with the comparison with our estimated model output, and we have observed the travel times in the particular interval, and it seems that this is nicely following with each other. Also, there are this diagram shows that for the trajectories, if I get the travel time increased by, let's say I have considered the travel time greater than 60 seconds, the curve is also following, and the travel time is actually agreeing with each other. This is error comparison. This graph is in the x-axis. I have the trajectories duration in an ascending order. So in the x-axis, this is in seconds, and the y-axis, I have calculated the normalized error for that, and it seems that in the time limit within less than 25 seconds, it seems to be very erroneous. But as the time axis increases, the data have less error. So this is a very good observation in terms of while predicting in a microscopic scenario, I might get erroneous data in the smaller interval of time. But as the time gets increased in the trajectories, the data showing the results are showing very promising results. Okay, so we'll come to our future work, and this is the outline of the sections. We have the link travel time estimation from the link count data and link count estimation from the travel time data. It's a dual problem, and so here is the motivation. We need travel time important for dynamic OD estimation problem. This requires the privacy sensitive and expensive data that I have discussed earlier, and traffic count data are less privacy sensitive, hence we are considering it. Estimation of travel time only using link count data has not been done yet, and that is very important. And hypothesis is that the link count data is sufficient to calculate the link travel time in urban road network. So these are the research questions: how to estimate missing traffic count data, because we need all the counts data for a particular area of interest. How to estimate that link travel time using that data. Then we have the brief methodology, proposed methodology. We will first try with the linear dependency analysis using the graph topology with starting accumulation and dissipation on the traffic on the intersection. We will analyze the traffic volume pattern in the adjacent intersection for the missing link prediction data, and we use graph-based learning for the weighted directed graph. And this is the final method, canonical correlation analysis for the cross-variance matrices. So this is the last part of the future work, link count estimation from the link travel time, and the motivation is the same. Traffic volume is also important parameter to measure OD flow. So we need the traditional approaches use the sensor data. These are expensive, and those are also restricted to case-specific applications. Using only link travel time data to predict volume is very important. Hence, this is the defined hypothesis. Link travel time in a road transportation network is capable of predicting link count without using the prior information about traffic volume. And these are the methodologies that have been identified, defining parametric relation between travel time and flow density. The flow diagram we will be using for traffic flow density, traffic speed, and traffic volume. And the speed density, the VK diagram, QK diagram, and QV diagram relationship will be helpful for us. And then we will try to generalize and maximize the feature extraction using information theoretic approach. And then we will try to produce the transferable mathematics for this model. So this is the research plan that I have. Today is the confirmation seminar, and I have this is up to timeline to 2021, and these are the research output. I have a channel pending in the transportation, and I am also doing an internship at the Australian Road Research Board. So that will go from my side. Thank you for your presence.
Thank you, Shubha. Well, it was a